All right, in the interest of time, since we have to talk today, we're gonna get started. I know I promised pizza, and the pizza's not here yet, but it will be here eventually.
And
And
to get your pizza,
make sure to fill in that attendance form so that we can keep getting the money. We have two junior scholars today presenting on some interesting research on methods for Milky Way physics and all sky surveys involving dust, stellar structure of the Milky Way, etc., focusing on methods such as Gaussian processes efficiently built for large computations. So the first speaker is Ben Dutch, who's doing his PhD at Stanford, and who will be telling us about GraphGP, scalable Gaussian processes with Vecchia's approximation. Floor is yours. You have the first half hour. I encourage people to interact with questions. And then when you're running out of time, I'll start waiting so that we can switch to the next. Thank you very much, and the floor is yours.
Great, thank you. Yes, and please ask for clarifying questions in the middle. So yeah, I'm Ben, and I'm going to tell you about GraphGP, scalable Gaussian processes with Vecchia's approximation. Cool. So bit of context, science context, before we dive into the method. So this is the Milky Way. The beautiful dark splotches are dust. And for a long time, we studied dust in projection in 2D, but a big project in the field is to map it out in 3D so we can unlock a lot of new interesting science. And this is ongoing, pioneered by a lot of people here, as well as other places. And I selected two just recent 3D dust maps that have been made in a neighborhood around the sun. The one on the right is much bigger volume, kind of better posterior inference, higher angular resolution, much more data. And it's really good if you want to get extinctions towards like a target or something. But for ISM studies, people get upset about these big streaks that you see, which are due to how the errors are, parallax errors are mostly away from us. And if you just kind of naively do a per sightline analysis, you end up with these streaks. So the work on the left is much a smaller scale, but uses a 3D correlated prior, which says that you wouldn't expect things to be fluctuating much more side to side as they do forward and back away from you. And the result kind of looks like it has much more realistic cloud shapes. And one of the goals why we set out to do GraphGP is to enable doing this kind of stuff much faster at a much bigger scale. So what is this 3D correlated prior? That's where Gaussian processes come in. What's a Gaussian process? Gaussian process GP is a distribution of functions, so every finite collection of values has a multivariate normal distribution. Basically, this is a draw. This black line is a draw from a Gaussian process. If you took a bunch of draws and looked at the values at those two green dots, they would have a joint Gaussian distribution with some covariance. Often, the big question is what's the covariance that you choose? Often you have a sort of decaying, often the closer the points are, the more correlation you want to assume. That's how physical fields usually work. And the result is that you can get a smooth function. So that's why the black line looks smooth. And so a naive method to generate this black line is you go left to right, generating one value at a time, and each value you condition with Gaussian conditioning on all previous values. And this is actually equivalent to the Cholesky factorization. If you do like SciPy multivariate normal, under the hood, it's doing a matrix factorization, which is similar to this. But unfortunately, that naive method requires you to have an n by n matrix, and you have to do a lot of operations on the matrix. So this is basically a non-starter for these billion parameter maps that we want to make. Cool. So last background slide, Vecchia's approximation. This is from 1980s. The idea is, okay, when we go one at a time, rather than conditioning on all previous values, why don't we just do a couple of your nearest neighbors? And this is a good idea if your correlation is decaying with distance. Just want to emphasize, so, okay, say you're generating this value. Conditioning only on the green points doesn't mean you're truncating correlation at that distance, because those green points were also conditioned on the gray points in the past. So another way to say is the covariance matrix is like long range. This is a plot for a 1D example, x point versus x point, and it's logarithmically distributed. So that's why it looks much wider up there. The points are just closer together. And this is showing using only 3 neighbors, you get this long range correlation over hundreds of of pixels. And yeah, illustrating the point that for Vecchia approximation, the covariance is like a dense all-to-all correlation, whereas the inverse covariance, which is telling you about the conditionals, is sparse. Okay, that's all I'm going to say about background. Any questions so far? Setup, why, how? Yes.
I mean, you're showing that you have this long Right, you're showing that you have this long range correlation, but you must be still losing something about the approximation.
Yeah.
So can you quantify for us what you're losing and what level of long range correlation is lost because of this approximation?
Yeah, I'll have a slide later. So most of what I'm going to talk about is how to scale up this approximation and leaving the justification to, it's been used a lot, but I will have a slide somewhat addressing the quantitative stuff. Yeah, so the main point of GraphGP is to do this Vecchia approximation orders of magnitude more points than previously done. And I have three little pieces to that. One is pretty simple, how do you find these preceding neighbors quickly? How do you do this kind of conditioning in parallel so that you can do it faster? And how to fit this into as little memory as possible, which is usually the main bottleneck for us. So I'm going to.
All right, I'm sorry for a very basic question.
Yeah.
So when you say preceding, so you're going to approximate functions over time.
Yeah. So
it's not just spatial; it's over time.
So I'm just talking about spatial, but Gaussian processes can be used a function of any continuous variable. Another example would be like spectral dimension or something, and you could use it for all of those. Although we're targeting stationary Gaussian processes, so it's really if there's a distance. So it wouldn't make sense to have it, one point be space and one be time. Probably you don't want to.
So when you say the preceding neighbors here, for your particular problem, what do you actually mean?
Yeah, great. So when I said, this Cholesky or whatever, you go one at a time, and then you have to condition all the other things you've already fixed. So at each point, you need to find the neighbors, not globally, but amongst the points that have already been generated. So that kind of sequential business is one of the reasons why the parallelism is going to be a thing to think about. Yeah, but that's exactly on the nose. So neighbor search, we all studied forever. The standard solution is to build a KD tree, which partitions points into kind of quadrants and then can prune large sections of space, like throw out huge amounts of points on the basis that they could not possibly have a nearest neighbor because they're all more than X distance away. Now, that's what existing Vecchia approximations do. They look at a KD tree and then just filter the neighbors for which are the ones that are preceding. But this is not working at scale, because if you have 1 billion points and you want the preceding neighbors of the 100th point, you're not going to look through. It's a very small fraction of the points are actually in your KD tree. And if you naively do this neighbor search as people do, it's going to take forever. So there's various ways you could say to solve that. The way I think the fastest way that we use is actually to generate the points in KD tree order. So I made a binary representation of the KD tree here. 0 is this point, that's the top level of the splitting, and then they split from then on out. And then important observation we make is, okay, if you throw away, say 5 and on, the resulting thing is still a valid KD tree. So if you want to do the preceding neighbors of 4, you just pretend the rest of the tree doesn't exist, and you can just query in that KD tree. So what's the idea? Tree order is the generation order. I'll also just mention as part of this, we wrote a JAX KD tree, which didn't exist based on some GPU KD tree algorithms. And I'll also mention there's this cool new work. If you're into neighbor searches on GPUs, that promises to make this a lot faster. But at the time, this was the kind of state of the art. Great. So that's kind of preceding neighbor searches. We do it with this new proposed order. But now we turn to how to parallelize the computation. So luckily, since we're doing preceding neighbors, we have this graph, which is already in what CS people will call topological order, which means that the edges point always backwards. And so it makes, so this example, how should I say? These are examples of what your graph could look like. You have 1 point, conditioned previous one, or you could have a graph looks like this, where 2 points are both pointing back to one neighbor and they don't talk to each other. So in order to parallelize things, we want this one, not that one, because you can generate those two in parallel. And this is something that graph analysis knows how to do. It's pretty easy if you have a directed acyclic graph in topological order to find the batches that you can generate in parallel. Now, unfortunately, KD trees are terrible for this because they intentionally put nearby points in physical space near to each other in the graph order. And so you end up getting these long dependency chains. So we do a simple change instead of putting like the left and right children right next to each other, we put them maximally far away. So we insert the left children first for all the nodes and then the right child. This is also equivalent to bit reversal permutation, you know, like FFTs and stuff, but essentially, conceptually, what it's doing is just spreading out nearby points to far away locations in the tree. So, okay, bit of technical stuff, but long story short, this is a plot of how many batches we need and how many points can be in each batch. So that would be like, this one has 3 batches, this has 4, and this one, the third batch was 2 points. And the blue line is our order, which is beating everything else, including the random order in gray. The green is the KD tree, which is really terrible. And we've also put some other orders that are proposed in the literature, showing that we're better for that. And in practice, this is plenty good enough to saturate modern GPUs, and so it's very parallelizable. Any questions? I know that was a lot. Yeah. Oh yeah, go ahead.
Now you do.
Why is the random stuff good?
Yeah, so I mean, the thing you don't want is nearby points near to each other in the tree. So random order, 2 points in the sequence are just unlikely to be very near each other by random chance. But our bit reversed order is kind of maximally bad. Or like we're doing a really good job spreading points away. So that's why you have this hierarchy of like KD tree is bad, random is better, ours is the best. I think there was another question.
When you're changing the graph,
Yeah,
like the tree,
yeah.
you're just changing what the position in the tree means, but essentially it goes the same graph for information. That's a question.
Yes, good question. No, well, so it changes the meaning of the algorithm because the order that you condition the points, the neighbors are the preceding neighbors in that order, which change depending on your choice. So this does affect technically the approximation, though we'll have a plot. It doesn't really matter in practice.
Okay,
Yeah.
another follow-up, so it would yield the same partition, but in a different, with a different algorithm that makes it, like a different sequence of cuts.
Right. Yeah, the partition of points is the same, kind of. But I think the thing I would emphasize is the tree is not used in the definition of the algorithm, really. It's the definition of the algorithm is just what's the order of points, and then it's always the preceding nearest neighbors. So the concept of the tree is just more like a computational how you find neighbors rather than mattering for the algorithm, for the approximation.
Anyone else?
Yeah, I just want to make sure I understand
Yeah.
your goal here is to basically get a realization of a Gaussian process with some, and is there kind of a tacit assumption that the correlation function is steep, sort of like the nearby correlations matter a lot more than long range ones, so that you can just start kind of throwing down points and say, these are random, okay, as I start to fill in, I have to make sure I'm respecting the Gaussian process as I fill in, but like if long range things were really important, you'd have to really.
Yeah, Vecchia approximation will not work if the correlation function is not decreasing with distance.
Yeah, okay.
So,
But that's the only requirement? Like,
well, it's has
the
error.
comparison is pretty good, like that's
Yeah.
not the whole things we care about.
Yeah, I have I should have maybe put it earlier, but I have an accuracy plot. I mean, the quality of the approximation depends in a complicated way on how fast it decreases.
Yeah.
So,
Alright, we can talk about it
Yeah.
later, but okay, I thought there must be some.
there's just, we don't, like, there's not a lot of general statements we can make, but the answer is if it's not good enough, increase K. like increase the neighbor. Yeah. Okay, so parallelization done. Last part, a little bit more on the, I'm just gonna say, I don't have a lot of I don't want to go into a huge amount of detail, but how do we fit these conditioning matrices in memory? Usually, so we implement this in JAX, which you may be familiar with, which is kind of NumPy-like. And the thing that you need is a k by k, where k is the number of neighbors, conditioning matrix. And you need that for every point. And so naively, you need n times k squared. But you only need that conditioning matrix for a short amount of time in order to generate the next value, and then you can kind of get rid of it. So that's what we do. So we have a vanilla JAX implementation, which is easy to use right away, and then we also have a custom CUDA implementation, which basically does that on the fly conditioning for you. And I think this is okay. Let me just extend the class. This is how long it takes to build a graph, which you usually do once. So hundreds of seconds, or 10 to 100 seconds for this 100 million scale. And then forward pass is much less, less than a second at the 100 million scale for the numbers of neighbors that I've outlined here. And the biggest thing, I guess, you can see is this big offset between the JAX in orange and the CUDA in blue. And that's because JAX is using basically a factor of k less memory. And so even the scaling with k is much different. And yeah, so this is pretty transformative for the, you can go more than order of magnitude larger, and also simultaneously order of magnitude faster. One thing to note is the time here is, we're basically completely memory bound. The loading values from memory takes longer than doing the Cholesky factorization, which is kind of a usual regime you're in and why you want to use GPUs, at least for this small number of neighbors. Yeah, I think this is a compelling reason to want to go to CUDA to do some basic optimizations. Now, one reason people don't like to use CUDA is because then you lose all the autodiff of JAX. So we implement the derivatives in CUDA as well and link them up to JAX. So you can use GraphGP, the CUDA version, just like you would any other JAX component. And I think that's important when we're developing new high-performance code in the age of AI, is that we implement derivatives. Okay, so that's how to fit conditioning matrices in memory. And that's all that's kind of the complete GraphGP algorithm. I have one slide on accuracy. This is not our main focus, but I provided some test distributions. This is as a function of the neighbors that you use, what the KL divergence between the true distribution and the GraphGP distribution of functions is. This is for a test distribution of 10,000 points in a unit Gaussian, which has a couple of 4 magnitude dynamic range and an irregular point distribution. And it's for 2 Matern kernels, which is kind of like a power law with a Gaussian cutoff at the large scales. And yeah, okay, so what do you see? You see that more neighbors is good. You see that longer range correlation, which is the dashed line, is harder to represent. The KL, which is bigger, which is bad. And then I plotted a bunch of different orders, including this max-min order is kind of from the literature saying this is a better order to use for accuracy, which it is. You can see we are, all of our GraphGP lines are hitting the blue line, and we're slightly worse. But the thing that we argue is order is less important than other factors, including what kernel you use and especially the number of neighbors. By doubling the number of neighbors, you can easily offset that difference. And we are offering, more than order of magnitude more neighbors at the same memory usage. Yeah, so we focus on scale. And then just to give a little more integration, here are 2 toy examples of the types of kernels GraphGP. And so Vecchia approximation is known to be very good at doing power law, kind of power law kernels or power law power spectra. And so this is like a kinked power law in purple, and you can see we do pretty well with only 16 neighbors. This is just in 1D. And then something we do very poorly at is, say you put a bump in your power spectrum. You can see it's significantly below where it should be. And one thing to keep in mind here is that we're trying to use GraphGP, and people often use Gaussian processes as a prior, right? Not as so if you're a cosmologist, you don't want to be using GraphGP because you're using Gaussian processes as a summary statistic for your data. And you're not going to get the power spectrum quite right. But if you use it as a prior and say, you know, the only time you're going to fail is if you want to a priori assume there's a bump in a power spectrum in a specific place. If you want to assume a priori there's some kind of power law power spectrum and let the data drive, you know, where are the bumps, where are the special signals, that's totally fine. And like you can still represent fields that have bumps. It's just not going to be enforceable by the prior. Just for reference, you know, this is the type of prior that is often used in 3D dust map in the example I showed earlier in 3D dust mapping. Okay, any question about accuracy since I know there were ones earlier? Yeah.
So if you knew there was a bump there already,
Yeah.
would you choose a better order of preceding neighbors to try to recover performance?
My intuition is that you would simply need enough neighbors to kind of get over the bump. Because there's like kind of neighbors being chosen at all these different scales. And if the neighbors at like a larger scale are more important than the ones nearby, you need to get them. Maybe you could.
So like you could choose the nearby ones and then a couple far away ones, but you don't
Yeah,
have to choose all of the scales. If you knew the bump
Right.
scale, you might know
Okay.
how to choose some of those.
Yeah, okay, this is the answer. For a given, actually not even for decreasing power law, the k-nearest neighbors are not the best set of points to choose. Because they have this crazy global dependency. You actually want a distribution neighbor that's kind of isotropic around. So even in our case, we're not doing the optimal thing. There's work showing you should do something different, and in general, it's the same story. Doubling the neighbors is much more important than choosing that stuff. But I would imagine what you would want to do to enforce a bump is, yeah, optimize what neighbors you choose, and there'd be some faraway ones. And yeah, the downside there is then you've optimized for your kernel, and if you're fitting the kernel jointly, then you're done for. But yeah,
Okay, thanks.
any other accuracy questions? Sweet. Okay, so yeah, compared to prior work, so I have a laundry list of things. The iterative target refinement used to make the previous map I showed, kind of the only thing that's been able to scale to how our scales. So that derives points and neighbors from a grid. We can do arbitrary points. That ICR parallelizes by severing dependencies, whereas we just analyze the graph to find the batches without severing dependencies. And ICR doesn't have an inverse and log determinant available, which we do because of the graph and other reasons. But in many ways, this is a successor to ICR. The GPU, which is a existing GPU Vecchia approximation, scaled to around 1 million points kind of max because of how they've done neighbor searches. They also don't do a forward pass, so it can only really be used if you're directly fitting a GPU to data rather than as a part of a larger model. Well, there's some caveats, but basically it doesn't have a forward pass, and it's written in R with no octave. So yeah, and we don't have, so I'm not going to present a finished application, but I wanted to give you some sense of what I'm using this for, and what you could use this for. One thing I'm doing is working with SphereX data, which to make a map of the 3.3 micron PEH emission. So this is what raw pixels from a bunch of different SphereX images look like around the feature, and you can see there's this banding structure associated with their filter, how the filter works, and there's a lot of stars in there mixed up. And we're using GraphGP as a prior for the underlying pH field, combined with a model for the stars in PSF, and solving the Bayesian inverse joint Bayesian inverse problem, and leveraging, we're going to argue, leveraging that correlation allows you to, spatial correlation lets you do the separation much better, we're going to argue. And so how is GraphGP assisting in that? Well, the obvious one you can think is for the background, and I'll just take a, for the PH map, and I'll just take a moment to say GraphGP is a single GPU code, but the algorithm is very amenable to multi-GPU. We cannot very well do the graph construction multi-GPU, so you kind of have to like do that yourself. But once you do that, we're using GraphGP across 16 GPUs to do many billions of points, and we're going to do more. The other little thing I'll mention is we're actually also using GraphGP for the PSF. There's not yet a good PSF for extended PSF from SphereX, so we can fit both the very small subpixels stuff in the center of the core of the PSF as well as out to larger scales. And it's just really easy to prototype, right? You just like say what points you want your GP at and it'll do it. Of course, there are plenty of other ways to do that, but just to give you a sense of the flexibility. And then the other application I'll mention is many of you probably here know the upcoming VIA survey. So I'm a member of the VIA collaboration, and we are going to have a bunch of spectra that have sodium lines from the interstellar medium. And what we're going to measure these, and what you're expecting to see is around the region. This is one of the sodium doublets zoomed in. And this is a bunch of stellar spectra. All these lines are stellar sodium lines, and as a function of distance, you see the ISM component growing. So we can do sodium tomography in the ISM, with VIA, and GraphGP is going to be important to kind of being able to model the whole sky jointly with that. So with that, I'll leave up a little summary of all the nice features of GraphGP, and this is just a GIF showing arbitrary point distribution, many orders of magnitude dynamic range, representing a stationary kernel. So yeah, thanks.
Good. Questions? So if you go back to your this slide, so why is it important to make this sodium measurement, and how exactly you're going to use your architecture regression process to actually model sky view? What you want to do is to be able to predict this particular feature in any location of the sky from, I guess, will this be via data, or what exactly is the importance? Was the physical relevance?
Yeah, I should have said, I mean, this is being done with many techniques, but we want a 3D map of gas density and also velocity. So this allows us to tie density to velocity, which is going to be really cool. And how we're using, to make a 4D map, which is, any application of 3D maps, like galactic dynamics, star forming regions, we want to know what the dynamics is in 3D. And then how we use GraphGP, one of the challenges and why people have chosen to use hot stars, which are not very numerous for these kinds of studies, is because they don't have stellar lines. And so these have like stellar lines contaminating everywhere. So the point of GraphGP is we're going to be able to, just like with spheres, we're going to be able to leverage the 3D correlation in ISM sodium to help separate it from the signal that's in individual, the stellar lines. So GraphGP and Dr. Price generally are going to help with the separation.
Thank you. Yeah. Lisa? So please, sorry. Thank you.
Thanks, Ben. I understand more and more each time we hear about this, so thank you. But have you actually tried, I should know the answer to this, but have you tried to like remake Gordian Knopfler's map with this, and what happens if you do?
That's a good question. I have tried to remake Gordian's map with other techniques. I have not done it with this, but I mean, that's a good idea. Yeah, and it would be nice to show just how much faster it could be. Yeah. Good suggestion.
All right, I'll be distracted with the pizza, so I here. Anyway, any other questions? We have maybe 1 more minute. Or comments for Ben? Okay. Well, thank you very much this time, Ben, again, and Again, feel free to interrupt with questions, and in 5 minutes, it's over here, so that's good news.
And then do you have
All right.
you've got the mic, it's on.
Thank you, Robert. Always yours.
Yeah, good. That should work.
Right, yeah. Thank you for the introduction. I'm happy to present my work here today, which is about the stellar density of the Milky Way, for now in our close vicinity. And this work is done together with all these people. And as you already said in the title, I'm part of the Milky Way Atlas project, which is a project about creating the first map of the Milky Way with all its physical components. And of course, this is very ambitious, but when we look at what has been previously done, we can see, for example, as Ben already showed, the dust map, which shows the dust in within 1.25 kiloparsec of us, and is the one really good example of doing such reconstructions. But then, of course, one can go even larger. And for example, this gas map is a map of H1 and H2 of the whole Milky Way. But then one is not just limited to the 3D positions of different components, but one can also go, for example, shown here, to velocity space and make reconstructions of the velocity of dust in this example here. And then what one can also do is to build upon these maps. And for example, here, the dust map is used to then create a map of H alpha emission within the dust map volume. And in Milky Way Atlas, what we want to do is to make many more maps like these and also improve the existing maps. And my topic, as already said, is stellar density. So the most prominent thing when we look with our own eyes into the sky. And I hope that when you look at this image, you actually think about the stars and not the dust that you see there. And the nice thing with stars is that we have Gaia, which has the measurement of over a billion stars with incredible precision. And building upon this Gaia data then, I'm working on making a stellar density map, which is needed, for example, just thinking of the different components of the Milky Way to make a map of the gravitational potential or the dark matter density or the radiation field. But also then there are many more applications for such a map. I'm part of the information field theory group, in short IFT. And what we do there is Bayesian inference for fields. So at the center always stays Bayes' theorem, where we have two parameters in the formula. One is S, the signal field, so the thing that we want to reconstruct. And the second thing is the data. And then Bayes' theorem nicely gives us that we can represent the posterior distribution, so probability of the signal given the data we measure, through the likelihood, which is the probability of the data given our signal, and the prior, which is just the probability of our signal and the prior knowledge that we put into it. And then the models that we build look, for example, like this. On this side. And these models are then implemented in our framework, which is NIFTY, Numerical Information Field Theory. And you see it has different layers. So I quickly go through the different layers to explain to you what it is. The input, which always comes first, is our size and latent space, which is white noise. So just parameters drawn from a standard normal Gaussian distribution. And then we apply a correlation kernel to these parameters to then correlate the different positions. So you can see what here looks just like random noise that actually gets correlated, and you can see structures close to each other actually have somewhat similar values, and one can again much better represent what we want with our. And then one can combine many of those different ones to represent the field that we want to reconstruct, which then, for example, can look like this. And this is really flexible, so we can really build many different models and represent many different things as we want to do in Milky Atlas. And in whole, this part of the model represents the prior, so the knowledge we have a priori about what we want to reconstruct, and is one of the big parts of the model. And then second, we have the part down here, which is first here the response, because somehow we have to get to the measured data. So we have to implement something which maps these prior to what we then actually measure. So this response then connects, it gets as an input the prior and then connects it to what is actually being measured. And then the third very important part down here is the likelihood, where one then implements the statistics of the measurement process. So for example, if you just have counts, you have Poissonian statistics, for other ones you have Gaussian statistics, and this is all implemented then in the likelihood. And in total, then this part of our model gives us our knowledge about the measurement process and what we know about how we actually, the data is being measured. And very important, yeah, question.
So if I understand correctly here, with your signal, you mean the actual sort of underlying, function that describes the density of stars?
Yes.
That's what you're trying to refer.
Yes.
Is that correct? Okay.
So this S in my example, for me, is the stellar density. Yes.
Okay, got it. Thanks. Sorry, that's very basic.
Quite good. Thank you. So one very important thing is that the parameters which we infer in the end are always these size, because given all these size, everything else just flows down the model. And then we use different inference algorithms to get this size. One is MGBI, Magic Gaussian inference, which approximates the posterior distribution as a Gaussian. So you can see here in red an example for posterior distribution, and then we approximate this as a Gaussian distribution. But of course, you see it's not a perfect match, it has its limits, which is why there's also a second one, which is geometric variational inference, short GVI, which then goes further and actually does a parameter transformation from the space in which you have your posterior to a space where the posterior looks more Gaussian-like, and then it fits a Gaussian in this space to then be able, through the backward transformation, represent this posterior much better than with the other one. Now,
I was expecting a question there.
Well, I think the question hanging in the room is, should we pause for 5 minutes and get pizza? Because I'm worried that people can't focus if they're smelling pizza.
All right, well, I suggest people slow in an orderly fashion, slowly getting their pizzas and coming back to their seats. But yeah, let's give maybe a couple minutes. Sorry for interruption.
yes.
Thank you, Doug. That was definitely a very.
I'm just looking out for everything.
Like people still. We have limited time, so sorry for the interruption.
Yeah, sorry.
Please go ahead. Yes, a question.
So on the right here, this mapping, is this just kind of bijector mapping, or is it something more sophisticated than that, or is it just like a rotation translation matrix?
This one is a bijective mapping, and it's like how you derive this mapping is through the likelihood. For this, you kind of get an approximative mapping from one to the other.
And have you thought about using normalizing flows? That's like the perfect, like that's like a example of something like a mapping like this. But have you implemented anything like that, or is it just a very simple mapping?
So this actually is somewhat like a normalizing flow, but like the problem kind of in these applications is that we have millions degrees of freedoms, and their normalizing flows then become difficult, which is why we use this, which is then can much better handle these dimensions that we're dealing with.
And things like flow matching models or computing models, they don't scale to these dimensions either. Is it the...
Not as good as I think. No.
Yeah. Thanks.
Yes. So good thing we made a break, because then you could digest a little bit about how this whole model side. because now we move to my model, how I try to model the stellar density. And we have these two blocks. So first about the prior, what I use as a prior, I just use a three-dimensional correlated field in spherical coordinates. So helix times then logarithmically radial with space spins. And it's nice that we had Ben giving this talk because this is also generative with GraphGP. So I can also advertise this at this point. And then the important part is about modeling the measurement process. So modeling which stars Gaia can actually see. And for this, I take a dust map and then combine it together with a threshold map of Gaia. So a map of like a magnitude until which I assume that Gaia can see all stars, and then afterwards that Gaia can see no stars. This is an approximation, but at this point, to make it simpler and also then at later stages be able to derive a better likelihood, it's an approximation which helps a lot there. And then third, I take a luminosity function, so a function giving the probability of stars having a certain luminosity, to then combine this into a map of the probability of seeing a star at a certain position. So this is just a slice of such a map, and you can see color-coded like here's the most probability. And then if you move outwards, you can see the probability decreasing because, of course, stars get fainter, more distant they are away. So this is to be expected. And then also you can see very nice the imprint of the dust map, because, for example, down here, you can see that there are dust clouds here in front, and then they obscure our vision to the back here.
Sorry, so this is like a top view of on the galactic plane?
This is all locally 1.2 kiloparsec.
Okay.
Because it's restricted with the dust map volume. So this is locally and it's a slice along the set.
But the rates are radial, like.
And this is radial,
Yeah.
and then it's X and Y.
Okay, thanks.
Yes. And then this map, I combine with the prior to make a representation of the visible stellar density.
Yeah, sorry, one more question on the
Yes.
density is, I mean, you've sort of shown a counts map or probability, but you actually have a probability per stellar type, right? So at every given distance, you have a probability of observing a given stellar type, is that right?
Yes, one can do that. Like this is integrated, so it's just probability of seeing a star, but one could also expand this to have different luminosity ranges.
That might help you reject stars or objects with weird colors that are not consistent with your stellar densities, if you knew what the stellar type should be. Because you're not comparing with the geometry. I don't know what your data is yet, but you're not comparing with the geometry, I assume.
Yes, I expect come to it later in the data part, but it's just essentially positions and fluxes of stars.
Thank you.
Right, any more questions on this so far? If not, then yes. I combine these two to get this map of the visible stellar density. And you can see, for example, the imprints like here's like a little cutout, or down here it's a little bit less compared to the picture up there, which is then an imprint of this map of then what can actually be seen. Then the second very important part is the likelihood. Here I use first an ambient Poisson likelihood, so the probability for each individual measurement for the star to be at a certain position, having a certain flux given the prior knowledge, and then combine this with marginalization, explicit marginalization over the parallax error to account for the stars not knowing where exactly the star is, but only having basically a distribution of where the star is. And then as a third component, I have a Poisson likelihood on the total number of stars inside the volume to just fix this overall normalization of how many stars there should be. Because of just the first two, I can get a probability distribution of the stars, but not the overall normalization of how many stars there actually then are inside the volume. And then if you would put it into a formula, it would look like this, which is a lot. And the reason why I moved to this, to just explain to you what it actually does, because it's not a very easy likelihood, it's quite complicated. And now we come to the data. So the data I am using is the same one as in the underlying dust map, the realization of Gaia XP data. And now, of course, you want to see how it looks in practice. So this is a mock test where I generate a ground truth stellar density. And then I use this to draw a realization from it as with the ground truth and get simulate measurements of individual stars, which I then or the question, yes.
Oh, yeah, so only a subset of this 220 million were using the dust map. Are you using all 220 million, or are you using just ones with like very high quality parallax measurements, or how, like, which part of the John sample are you actually using?
So I'm doing this quality cut, which is also written in the paper one should use. And then I use basically only the stars which have a sufficiently high probability of actually being inside the volume, because since I'm limited by this 1.25 kiloparsec, it doesn't really make sense to put a star there which is 99.9% outside of the volume. Yes. So I draw this ground truth realization, then generate data from it, and then I use this data to reconstruct again what the ground truth was. And you see here in the middle this likelihood I explained to you, which I implemented, and as a comparison, just a Poisson likelihood of just spinning stars onto the grid and then using Poisson likelihood to reconstruct the density. And you can clearly see that this likelihood here much better captures the fine structures, because, for example, in this region down here, there's like very sensitive structures, and it actually recovers it quite well. But when you compare it to just the Poisson likelihood, then you see that everything here is much more blurry because of the stars having uncertainties and not being in the correct bin, and then everything gets more blurry. Question, yes.
But we're looking at this kind of distorted as a top-down view of a sphere, so the edges are very low density because you're integrating through less column because you're looking at a sphere. But like, how should I understand this color bar in terms of orders of magnitude of fluctuation in 3D stellar density? Do you see what I'm saying? Like, it's blue near the edges, but that isn't actually telling me the overall
Well, it's
fluctuation.
blue near the edges just because it's like one draw from the prior. Since the prior is just a correlated field, it doesn't really. It doesn't include if it's like blue near the edges, because like the prior can represent anything. So it's just a coincidence kind of that it's blue there.
But I guess what I'm saying is this is a 2D projection. How have you done this projection? Is it a sum? Is it a
This is a slice.
Oh, it's just a slice.
This is just a slice, yes. Sorry, I should have mentioned this.
Okay, thank you.
We now go to projections. So I'm sorry, this was just slices through the x direction here, and this is a projection. So integrating over the x direction in this case. And you again see here these different fine structures. And then if you compare it, you can see them quite well here in detail. But here, then again, it is quite blurry. So any questions about this? If not, then now we can have a look how it looks with real data. And as you know, if one goes to real data, it doesn't always look great. So don't look at this and get anything of like, oh yeah, this shares this or this. It's work in progress. And of course, this doesn't look great yet, but it does show some things which look promising. Like these are such slices again, just to make it clear. Like you can see something which one could say it looks like more or less like a bar, but then again, there are a lot of artifacts in here, which we still have to figure out where exactly they come from and how to fix them. But also if one looks at the projection, now you probably already noticed the rings. These come from the spherical structure that just, if one takes the projection, then one can see these rings. But again, one can think of this as somewhat disk-like structure to just motivate that it does at least something or which goes into the right direction. And then just as an outlook of what one can also do with similar techniques is go into to combine this with stellar modeling. So what I show here is when one takes as a prior just a two-dimensional correlated field and then just takes data of stars inside a given volume and then reconstructs from the measured magnitudes and color magnitude diagram. And then one can, of course, combine this into stellar modeling and everything. So just as a small outlook of what one can also use this for. So in conclusion, what you should take away from this presentation is that this explicit marginalization that I do in the likelihood actually improves it and improves also then the underlying reconstruction. But also that the mapping of the stellar density, which I aim to do, even down to like very small scales, might actually be feasible. And then at last, just a bit of promo. Our package Nifty, which everything this is done in, is great for doing reconstructions like this and do Bayesian inference for fields. And it's open source, so check it out, please. And now thank you for your attention, and I'm also happy to answer your questions.
Question? Yeah.
So with this framework, are you able to calculate the evidence so that you can see how influential your prior is on your recovered posterior?
Yes, one can also compare models and calculate evidences for these models.
Okay.
There is something for that also implemented in Nifty.
Thanks.
Can you go back to your, oh, sorry, was there a hand? No. Can you go back to your applied to real results, previous one, this one? So what is it that we're actually seeing here? So you said this is, I said this is kind of a Y, Z, so this is above and below the galactic plane. And what is it, what is this structure we're seeing? Is that related to the actual plane of dust across the, on the galactic plane? Is that what you're seeing in this sort of plane-like structure? I guess my specific question is why do you expect, if this is because of attenuation of the dust in the plane of the galaxy, but you're still seeing a smaller density of stars, is that just because you're biased?
Do you mean this here?
Yes.
It is one of the artifacts I'm talking about, where just something doesn't really go correct at the moment, because the algorithm thinks it can see more stars than it actually can in these regions, and then probably puts a lower stellar density there. And so, yeah, it's not something you should interpret too much, because this is still work in progress and I'll thank you a lot.
Fair enough.
Yes.
Thanks. Yes, there's one in the back and then.
This might be related to Andrew's question, but I guess does the likelihood take into account like it's easier to see a red star through the dust? And I guess follow up on that is like, are you doing a comparison of like, I include the dust map versus not? What do the reconstructions look like?
I've not yet done a comparison of like completely not taking dust into account. I would expect it would something somewhat similar to this, because I think especially like stuff like this is kind of where something goes wrong, and it would probably look somewhat similar to this. And your first question, I've not so far taken into account like that one can see better certain stellar types than others. So it's just about this probability distribution and nothing else at the moment.
Okay, so one question is how far you can push this in resolution. I mean, theoretically, one could see stars, star clusters pop out here in terms of the counts that people get in these catalogs. You seem like you're targeting a much lower angular / spatial resolution. Have you tried to look at test beds like that, and does it work well, or is it too far away from the prior?
So this at the moment is at a lower resolution, just to be able to somewhat quickly actually see results and see if something works. But in the end, the aim is to completely resolve GaiaXP. So to really go to high resolution.
So you should see all the clusters.
So you probably should see individual clusters, yes.
Anyone else? I did. Okay, well, let's thank both Ben and Robert for nice talks today. Still plan to fill in the attendance so we can get the money. And are you guys around the week? This week? Okay, so where are they sitting, or in case people want to talk to them?
They're P106, which is the conference room.